morning. Don't make me yell today. Apparently there's a cold going around campus.
And you have generic cough
and I got it. I guess if you need a cough drop, let me know.
Do they sponsor you?
They don't sponsor me, but for all your cough drop needs, I recommend CVS Health Run. So we're getting close to having the exams done. My grader brought them in here. I was like, oh my God, they're gonna see these, and they're not getting them back. Don't do that.
Don't scare us.
So I don't have numbers yet. It's lower than the other exams. I might have missed the mark slightly on that one. Does that mean that the grade distribution is going to change at all? The grade distribution is not going to change at all. It's going to stay the same as usual. So we'll get that all sorted out. What I'd really like to do is before you take the exam, we'll see how much time I have. What I'd like to do is give you an idea of what your grade is going into the final. So that way you kind of at least know where you stand and you can have a little bit. Again, that's going to be a rough estimate because the final counts for how much? 40. It's 40%. So hopefully that's not news to anybody. That's been posted for a while. It's not news. It's not news. It's just scary. Again, that gives you a chance to bring your, to really wipe out the rest of the semester, really. So you can come into the final and crush it and make up a lot of points. So, I learned a lesson this weekend. What lesson? So it was like Saturday night. It was about 9 o'clock, and I was already, where were you guys at that point? I was in my pajamas. And so I decided, or my wife and I decided that we needed to get some dinner. And so what do you do for dinner at 9 o'clock on a Saturday night? Pizza. Pizza. I chose Chipotle. And so I didn't, I don't know. I wasn't thinking about it, but here I am. I was wearing my pajama pants and like an XL t-shirt, maybe 2X, like down to my knees almost, and some Crocs. And I walk in and I see at least 5 or 6 of my students at this point. In which, all right, I guess next time I should just put pants on. I don't know. So I'll have to be careful with that. All right, I guess let's get started. Exams, those will be coming back Wednesday. They're pretty much graded for the most part. I just gotta do a little number manipulation to make that all fit in for the semester. So that'll happen. Okay, so today, man, when's the final?
Tuesday.
Next Tuesday. Dang. Yeah. So there will be material on Friday. I mean, look, I've been through the blowout thing. I get it. I've been through it pretty roughly. But that said, it's still, we only have so many lectures. I post notes in a podcast. Get on it Saturday if you can't make sense of things Friday. So yeah, we're gonna be doing some new material, but largely what we'll probably be doing is we're gonna go over some alkyne reactions, I think, on Friday. And alkynes react very similarly to alkenes. So a lot of it's gonna be review anyway, and then we'll do a couple of new ways that we can react alkynes, and that'll probably be fun. We might blow some stuff up too. I don't know. We'll see. There's been a real lack of blowing stuff up this semester. All right, so today, let's see. I think last time we briefly defined that there is some stereoselectivity in these reactions. Yeah, so we said that there is stereoselectivity when we do an E2 reaction. So we came up, or we defined the word anti-coplanar, which basically means that our hydrogen being eliminated needs to be 180 degrees from our leaving group. And so you can see here, that's what that means in the Newman projection, where it's most obvious. It has to be on the other side and just in the same plane. So anti-coplanar. All right, so we'll continue from there. We'll take a look at an example. So our example, we're going to have this molecule. this with, let's say, sodium methoxide. All right, so sodium methoxide. First off, what kind of alkyl halide do we have? Not tertiary. Secondary. All right, so we've got a secondary alkyl halide. And so then we've got sodium methoxide. Now this is the tricky case where we've got to think about that pKa. And so sodium methoxide, is it going to promote an SN2 reaction or an E2 reaction? Yeah, it's going to promote E2 because its conjugate acid, methanol, is going to be around 17, which makes this a very strong base. And so we're going to promote the E2 mechanism. Now, in our alkyl halide, do we have a beta hydrogen?
Yes.
Yeah, sure. So we've got a beta hydrogen right there, and so that can be eliminated. But have we fulfilled the requirement that that beta hydrogen be anticoplanar? No, and so in fact, if we looked at a Newman projection of this, so in our Newman, we'll look down this bond right here. What we're going to have is, of course, our hydrogen straight down in front, and our bromine also straight down. And so that's not gonna work because they're not anticoplanar in this case. In this sense, they're now syncoplanar, and we're never going to do that elimination unless we are anticoplanar. Yeah.
So for it to be 180 degrees in the original molecular projection, it needs to be in the top left quadrant, so to speak.
Yeah, so we'll take a look at it. Basically, what we're gonna find is we have to do a bond rotation to get that into the correct conformation. All right, so then in the back we've got our bromine, hydrogen here, and methyl here. So what are we gonna have to do? Well, I guess I just said it.
Bond rotation.
Yeah, a bond rotation. All right, so we're gonna do a bond rotation, and specifically we're gonna do a bond rotation to make anticoplanar. And so to make it anticoplanar, basically what we can do is we can take this hydrogen, we can put it in the same plane of the paper, we just want it going up so that it's now anti. And so when we do our bond rotation, we'll now have this in a conformation where our hydrogen is up. On this carbon right here, what is now on a wedge? Yeah, so we're doing a 180-degree bond rotation, so stuff that's up and on a dash is going to be down and on a wedge, so our methyl is now on our wedge, meaning our ethyl is now on a dash. And so we'll keep everything on the right side the same. So we've got bromine, and then methyl, and hydrogen. So now what we do is if we view this thing in a Newman projection, what we're going to have is our bromine is down, but now our hydrogen is straight up, and so we've got hydrogen, bromine down. So now we can see that those are anticoplanar, just as we drew in the original picture. We'll go ahead and complete this picture. So we've got ethyl there, methyl, hydrogen, methyl. Okay, so now we've got anticoplanar. And specifically, when we say anticoplanar, we're talking about the hydrogen, and we're talking about the leaving group. So now those groups are anticoplanar, so we can undergo our beta elimination. So we treat with our sodium methoxide. So what that does is we're going to, of course, eliminate our hydrogen with a mechanism that goes as such. And so we're going to find that we only end up with one product. And so what we'll do is we'll keep everything on the wedges and dashes. So we have our ethyl group on a dash, our methyl group on a wedge, and then, let's see, methyl dash, hydrogen wedge. And so is that the E or the Z? That is the Z, right? So we've got our higher priority groups, the ethyl and the methyl on the same side, and so that's going to be the Z alkene only. So we are going to find stereoselectivity when we do these E2 reactions because we've got to make sure that we're in a conformation such that we can, such that we're anticoplanar and we can do the beta elimination. All right, so what you'll find is typically this is going to be most obvious if you only have one hydrogen or one beta hydrogen. That's the cases where you're only going to get one isomer. Now, if we had two hydrogens over here, then we have two possibilities of elimination, and so the stereoselectivity won't occur. But in this case, where we only have one beta hydrogen that can be eliminated, we'll only get one of the alkenes. All right. So let's take a look at how this impacts a ring. So our next example, what we're going to do is we're going to take something like cyclohexane. And so we will react that with sodium methoxide. And so in cases where we're going to use cyclohexanes with leaving groups, we're going to have to do a little bit further analysis. And so that analysis is going to involve some chairs. So we've got to go back to it. This is actually a good review because you're going to have to draw some chairs on the final anyway. So we must consider chair conformation. And sometimes this can impact things, and sometimes it won't. But we've just got to make sure that that we're going to be able to do this. So if we draw out one of the chair conformations, what we're going to find so let's number our stuff. So we'll just call we'll say 1, 2, 3, 4, 5, 6. So that's 1, 2, 3, 4, 5, 6. So I'm going to start with the chair conformation where the chlorine is equatorial. And so I'm just going to draw in any possible beta hydrogen. So these two are possible beta hydrogens. And then these two are possible beta hydrogens. We also have one, I guess, alpha hydrogen that we're showing that is connected right here. But that's never going to do any elimination. It's got to be beta hydrogen. So when we look at this chair conformation, are any of those beta hydrogens going to be anticoplanar?
Yeah.
Which ones do you think? So think about where these equatorial hydrogens, and I should have brought my model. Think about where these things are actually in space. And so this chlorine is going out to our right, and this equatorial hydrogen is going out to our right. And so if they're going to be anti, they've got to be 180 degrees from each other, right? So those equatorial ones are definitely not going to be anticoplanar.
What about the anti one on the third carbon?
You mean this one? All right, so again, they've got to be directly away from each other, right? So if we've got our leaving group straight up, that means that we've got to have a beta hydrogen that's straight down. Or if we've got a leaving group that's straight out this way, we're going to have a hydrogen straight out this way. So do any of these hydrogens qualify? They don't. So what we're finding is when our leaving group is in this equatorial conformation, we're not going to be able to do an E2 reaction because there are no anticoplanar beta hydrogens. All right, so let's write that down. We'll say that there are no anticoplanar beta hydrogens, and so importantly, that means there's going to be no E2. And so in this very simple substrate, it's not a huge deal, but what we're going to find is that it is going to impact things as we have more complex systems. All right, so of course, we have this chair in equilibrium. We have this chair in equilibrium. So the other chair conformation, we'll flip our headrests and our footrests. And so now we've got 1, 2, 3, 4, 5, 6. The chairs bring back good memories or bad memories? Okay, good. I hear it's a mixed bag. All right. So now our 2 carbon is going to have our chlorine down. And so we draw in all of our beta hydrogens. And so now that we've got our chlorine in an axial situation, do we have any anticoplanar beta hydrogens?
We have 2.
Yeah, in fact we have 2. We have this one there and we have this one there. And so the 2 important pieces of information here is that first off, I guess we've got it's our alpha carbon, which makes this a beta carbon, and that a beta carbon. So we're looking at the hydrogens off of those beta carbons. And so those are our beta hydrogens. And so since our chlorine is straight down, if we've got any hydrogens that are essentially straight up, that's going to qualify for anticoplanar. And we see, in fact, in this case, we do have 2. So in this simple example, we're going to have 2 anticoplanar beta hydrogens. So in this case, E2 is possible. All right, so for one thing, we need to draw out our chair conformation to just make sure that an E2 reaction is possible whatsoever. There are certainly substrates where no E2 reaction can take place. If we had an example like that, let's say I give you a substrate where we can never have any anti-coplanar beta hydrogens, and then we hit that with sodium methoxide, what reaction is going to take place? Not SN1.
SN2.
SN2, right? So in that's one case where, well, if you can't do E2, we've still got a good nucleophile, and so we would expect an SN2 reaction to take place. FYI, we're going to draw a really nice and neat flow chart once we get done with this to simplify all these decision making, or decisions that we have to make. So don't know if we'll get to that today, but it's coming up. All right, so in this case, we can do E2, and so we will. How many products can form? Really just one, right? Because it would be this plus this.
That's the same thing,
And so that's the same molecule. So we're only going to have one product in this case. All right. So let's look at that more complex example that I'm talking about. So in this case, we'll take a look at another chlorocyclohexane. So now we're going to put our chlorine down here, and so since we're going to have multiple substituents, we've got to show chirality. And so we'll say that our chlorine is the bottom one on a wedge, and so we're just going to have a methyl group on a dash. All right, so again, what we're going to do is we're going to hit this thing with sodium methoxide, but yet again, we're not going to just look at this and say, well, there's two things possible. Now let's see what happens if we did that. Let's just pretend that we're not doing our chair analysis. I would look at this and I would say, well, it would seem, all right, so seem that this would be possible, and it would also seem that this would be possible. And so let's see if that's in fact the case. All right, so we need to draw out our chairs yet again. And so when we draw out our chairs, let's see. We'll make this our chlorine, which makes this our methyl. And so our beta hydrogens are there, there, and there. We'll go ahead and fill in our alpha hydrogen as well. Okay, so just like the case above, do we have any anti-coplanar beta hydrogens? We do not. And so no E2 elimination can take place here. So we'd say no E2 possible. But we need to think about our other chair conformation. So our other chair conformation, flip our headrest, flip our footrests. So let's see, our chlorine's now straight up. We've got beta hydrogens here. So then we've got a methyl group there and a hydrogen there. All right, so are there any anti-coplanar beta hydrogens? Yeah, there's just one though in this case, right? So we've got this one right here, which is certainly beta, and is certainly anti-coplanar, but now in the place of where we had a hydrogen, we don't have a hydrogen anymore, we have a methyl, right? And so can we ever show a chair conformation that would provide us a way to make this product right here? No, because if we're going to make this product, we're essentially going to have to eliminate this hydrogen, right? But you can see that in this chair conformation, well, it's not anti-coplanar. Over here, you can see it's axial while our chlorine is equatorial, and so they're never anti-coplanar. Because they're never anti-coplanar, we're never going to be able to form this one. So this one is, we'll say never forms because we never have, that's a box that is too small, anti-coplanar beta hydrogens. And so in fact, we're only going to see one product form, and so it's going to basically result from elimination here. So if we have our sodium methoxide, go down here, and voila. So we are able to form this product. So we'd say that this is the only product that forms. All right, so when we have these, when we have leaving groups in in cyclohexanes, we've got to do a little more analysis. Think about, do we actually have any beta hydrogens that are anti-coplanar before we can actually do the reactions? And I'm pretty sure there's several examples of this on the last problem set, which is due when? Wednesday. Yeah. Yeah.
I just wondered, is there any
I mean, certainly we studied back when we were doing chairs. We looked at some of these, and we could figure out which would be the more favorable chair conformation. But it's almost always an equilibrium, right? And so unless we've got some really complex bicyclic system that we keep trapped in place, we're going to be able to form the other chair, right? It's going to be able to undergo that chair conformation. It just might not exist in that chair conformation very much. So in those cases, let's say you have two conformations, but only one of them can do beta elimination, and that one happens to also be the minor chair, right? It only exists 1% of the time. The reaction's not going to go very fast because it doesn't exist in that chair conformation very much, but it will still happen. So, yeah. Okay, and we'll skip this last example. Okay, so that is E2. Hooray for E2. Hey. Hey. Alright, so we'll go on to Roman numeral 3. And so this is going to be our stepwise mechanism, which is specifically given the name E1. And so it's just like SN1. We're going to find that E1 and SN1 are like really, really close buddies. They pretty much never occur independently of each other. Anytime we get E1 products, we'll get SN1 products. Yeah. So basically the way that you're going to do this analysis, the first thing you do is draw out what the possible chairs are. And once you've got the possible chairs, think about which ones can do beta elimination. And so this one can never do an E2 beta elimination because it never has anti-coplanar protons, right? However, this one does. But unlike the simple cyclohexane case, we see that it only has one, right? And so that means we're only going to be able to undergo the beta elimination in one position. And so since it's on basically the other side is the methyl group, we're only going to get this product. We never have a chair conformation that can lead to that product.
Okay, so since the double bond rate is so the first one. How do you do that?
Yeah, and so basically, what you can do, maybe the easiest way is just to number. It's usually a good idea to number things. So, for example, we can say 1, 2, 3, 4, 5, 6. And so that would make this 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And so what we can see is, since this is the only beta elimination we can do, we're going to form the product with the double bond between 3 and 4. And so when we go back up here and number, we would say 1, 2, 3, 4, 5, 6. And so we're never able to form a double bond or a pi bond between 2 and 3. All right, so the stepwise mechanism, E1. All right, so we'll talk about the kinetics. And so one thing we'll say is that like SN1, it proceeds through a carbocation. All right, and so if it proceeds through a carbocation, what we're going to find All right, so it proceeds through a carbocation, and what we're going to find is that means that the rate is going to be equal to K times the concentration of what? Alkyl halide, right? And so the nucleophile doesn't come into, or in this case, the base isn't going to have any impact because the first step is going to be the leaving of the leaving group, and so that's the only thing that will impact the rate. So, and yet again, we see that we've got a unimolecular process. And so in our unimolecular process, that's how we lead to the name E1. Okay, so mechanistically, let's take a look at this. And seriously, it's not going to be tough to distinguish between when E1 will happen and when SN1 will happen because we're just literally going to make no distinction. If you do E1, you're also going to do SN1 and vice versa. And that's because they both go through carbocations. Once you have carbocations, these things are so hotly reactive that they're going to do anything possible to become not carbocations. And so both pathways will work. So for an example of that, we'll look at tert-butyl bromide. And so what we'll react that with is just water. Okay, so of course we always want to try to do SN2 or E2 first. Biomolecular processes are our goal. Well, in this case, can we do SN2?
No.
Why not? Yeah, so in this case we have a tertiary alkyl halide, and so that means no SN2. But we can still think about E2, right? E2 can take place at a tertiary alkyl halide. But do we have a strong base? No, we don't have a strong base. So the conjugate of water is hydronium with its pKa minus 1.7. So that's way, way, way below 11. And so we find that our water here is not only, let's see, we'll just say that it is a weak base. So because it's a weak base, we're not going to have any E2 stuff take place. And so the only possible thing that can happen at this point is we form a cation, right? We can't do SN2, we can't do E2. And so that's what we're going to do. So we go ahead and show that leaving. And so when it leaves, of course, we're going to end up with a tertiary carbocation, which is pretty damn stable, right? Like tertiary carbocations are very, very, very stable. And so, of course, we've still got our water in solution. All right, so there's our tertiary carbocation. We've got our water. Now, do we have any beta hydrides that could go under, be beta eliminated here?
Well, in reference to the Lewis group.
Yeah, but so when we talk about beta hydrides, of course, we're saying that our carbocation is the alpha position, and so that means carbons connect to it will be the beta position. And so you can see we've got 3 beta carbons. We're just going to look at one of them. Do we have hydrogens off of that carbon?
Yeah.
Yeah, sure. So we've got that hydrogen right there. And so we no longer need a strong base to do this beta elimination because, again, how stable are carbocations? They're not stable very much at all. So they're going to do anything possible for to become stable again. And so in this case, our water can come in here. And even though it's not a strong base, the carbocation doesn't care because it just wants to become not a carbocation. So what we'll do in that case is this sort of mechanism. So we end up with our double bond, and it looks like this. We've undergone beta elimination, but we clearly haven't done an E2 mechanism. This is a stepwise mechanism. We've gone through a carbocation intermediate. But this, of course, isn't the only thing that could take place because we've already seen what other reaction have we learned that could happen at this point? SN1, right? We've got a carbocation. We've got some electrons on the water that could donate to the carbocation. And so, alternatively, we could have attack directly to the carbocation. And that would lead to an SN1 product. All right, so now, and of course, eventually we will deprotonate to get to our alcohol. So what we find is that we have an E1 product that forms, but we're also going to have an SN1 product that forms. And so what we want to do is we'll put this in a box and we'll say keynote. A carbocation type mechanism, so something that proceeds through a carbocation, if possible, almost always leads to both E1 and SN1 products. And again, that's just the downside of carbocations, right? I've said this since we started talking about it. Carbocations lead to really messy reactions. That's because they're so highly reactive, they don't have chirality, and of course, what else can happen with a carbocation? 1, 2 shifts of some kind, alkyl or hydride. And so, really, carbocations are super messy. So I'm never going to ask you to distinguish between an E1 and SN1 reaction because it's really hard to distinguish in the first place. You're typically going to see both of those things occur. All right, so leads us to letter B, which is regiochemistry. And so this is pretty straightforward. So the regiochemistry follows Zaitsev's rule. You guys remember Zaitsev's rule? Of course. The more substituted alkene is favored. All right, so that's just like E2. We're gonna have a major product that is the Zaitsev product, and then a minor product, which is the other product. So as an example, let's say we've got this, and so we're ignoring stereochemistry for the time being. All right, so we've got chlorine. So we're gonna hit that with methanol. Really, the thought process, look to do SN2 or E2. Can we do SN2? No. No, why not? Yeah, we have a weak nucleophile, so SN2 is not gonna work. Can we do E2? What do we have to do E2? What kind of base? Strong. We gotta have strong base. Is methanol gonna be strong base? What's the conjugate of methanol? It's gonna be very similar to the conjugate of water. So we're gonna find that we've got methyl and then a positively charged oxygen, right? And so is that gonna be a pretty strong acid or a pretty weak acid? All right, so water, its conjugate acid is hydronium. So hydronium has a pKa equal to around minus 1.7. Is that a strong acid or a weak acid? It's a pretty strong acid, right? Are these two things similar? Yeah. They're very, very, very similar. I don't know the pKa of this, but we're just going to say that it's around minus 1.7. Very, very, very similar. The only difference is a hydrogen swapped out with a methyl. And so, is that going to make methanol a good base? It is definitely not a good base. That's the conjugate of a strong acid. So, all right, we can't do SN2. We can't do E2. No SN2. No E2. And so we're going to have to do a beta elimination. Now let's see, where are our beta positions? So we've got one beta hydride there. And we're also going to have a beta hydride there. Alright, so we've got two possibilities for elimination. If we eliminate the blue beta hydride, we're just going to extend this on over. Ah! Alright. I just thought we'd play some music. We're sorry for crashing. It's okay. Alright, did we do this right last time? Recover. Recover.
Oh, no, wait. Oh, no. Oh,
Control Z.
I'm doing it.
no.
Let's see what happens if we sync it.
You just sing like me.
I mean, I'll have the notes.
Wait.
No, that's...
No,
that's...
Just look at crap.
We're just going to continue. You have it in your notes. I'll also have the 11 o'clock notes that I'll post. And I also have the recording thing, so we're good. It's fine. It's all there. It's just going to be slightly different. All right. Let's remember, it's not recover. Or it's not...
It's reload.
It's reload is the... All right, so reload. Whatever. All right, we've already wasted too much time. Okay, so we've got two possible products. I think the blue one. Yeah, so that was the blue one. So we've got that product.
Can you just read all of it?
Oh yeah, good idea. You guys are smarter than I am. Chlorine, hydrogen, hydrogen. So we were using what, methanol? All right. This seems to be happening more and more. I don't know. All right, so the other possibility is we eliminate the red hydrogen. And so in that case, we have that. All right, so according to which is the Zaitsev product?
The blue one.
Why is it the blue one? Yeah, but so the blue one is tri-substituted, and so that's going to be the Zaitsev product. And so that also means that it is going to be the major product, and the red one will be the minor product, and we can call it a good day's work. Okay, oh, by the way, here's a perfect chance for me to add this. How many eval emails have you guys gotten? Yeah, a lot. So anyway, I might try to find some class time because I really want your evals. But I thought I'd make it into a competition. So 10 o'clock, I've had 30, and this is, what a great exam to give at eval period, right? All right, so, 10 a.m., 38% of people have filled it out. 11 a.m., 39. It's not my fault. All right, so, yeah. Oh, I will say, in 103 last semester, I got 80%, which is pretty good. So, all right, moving on. Extra credit. If everyone does it, it defeats the purpose. But okay. So that is one thing about the regiochemistry is that again we're going to have the Zaitsev product, or we're going to have a minor product. But we can also see cases where, so since we're going through a carbocation, so shifts can occur. And so we should be pretty comfortable if we were given something, say, like this. So let's say we've got this alkyl halide, we'll make that a phenyl group. So let's say we react this thing with methanol, and so we end up with a product that looks like that. All right, so it may not be immediately clear how we get to that product. Well, certainly not without the double bonds. All right, so it might not be immediately clear how we get to that product, but we can figure it out. And so I've said this several times, but if you're given a mechanism and you don't know how to get to the product, think about what reaction or what type of mechanism it goes through. And so in this case, what kind of mechanism does it probably go through? Yeah, in this case, probably carbocation. It's written right above it. And so what we're going to go ahead and do is just get to the carbocation and then figure out how you can make it work. All right, so if we do that, we get to our carbocation. So this is our carbocation right here. So of course from there, what can we do to maybe, well, all right, so let's think about going just directly from this to this. All right, so that would mean forming a double bond at this position right here. But are there any beta hydrogens which we can do that with? Yeah, there's not, right? Because we've got two methyl groups here. So this is a quaternary carbon. There are no protons which we can do beta hydride with. So what are we going to do instead?
Shift.
Yeah, so we're going to have to do a shift. So in this case, we're going to do a 1,2 methyl shift. And so we'll take one of those methyl groups and we're going to shift them over to the carbocation. So by doing so, we're going to end up with this carbocation. Is there a reason for that to happen?
Yeah, because it's
Yeah, so thermodynamically, we've increased the stability of our carbocation. Not only is this tertiary, why is this going to be an incredibly stable one? Yeah, you've got the phenyl ring nearby that can also undergo resonance with the cation. So it's a very stable carbocation. So finally, we have our methanol. And so we don't really care too much about it being a weak base because we've got a carbocation. And so we will eliminate as such. And so that leads us to our final product. And so in these cases, certainly you might think, well, why don't we eliminate there? And you could eliminate that primary beta hydride right here. But this is a mechanism question, so all we're asked to do is go from here to here. You don't have to worry about other pathways. We want to think about the pathway that will lead us from starting material to product. All right. So finally, we get to C. That is stereochemistry. All right, so one important difference between E1 and E2 is that an anticoplanar beta hydrogen is not necessary. All right, so it was necessary for our concerted mechanism, but we're going to find that that's not the case when we do E1. And we'll show you why that is in a sec, too. All right, so that means that there's no selectivity, and so typically we'll find that both E and Z alkenes will form, which is unfortunate. Again, just another downside to carbocation stuff. All right, so if we have an example, we'll show, let's see, we got methyl. And so we don't care, we'll show a syn coplanar, it doesn't matter. And it doesn't matter because the first step doesn't even involve that beta hydrogen. The first step is just the leaving, right? So we have our bromine leave, and so when our bromine leaves, nothing happens on the left side. We'll keep its chirality intact. But what we're going to end up with is a carbocation, which of course has what kind of hybridization? sp2, making it trigonal planar, and so it's trigonal planar because we've got this big wide open p orbital that will draw straight up and down, and so that means that we'll have a trigonal plane where the ethyl's going back and the methyl's going forward. And so what we're going to find, because let's think about what's really happening if we do this beta elimination. So if we have some base come in here and deprotonate that proton, we're going to have a lot of electrons which want to form a pi bond. And so sure, it does have to be coplanar with a p orbital. In this case, though, it's got two options, right? So are these electrons currently coplanar with a p orbital? Well, this p orbital is straight down in the plane, and I didn't say anti-coplanar. I just mean coplanar, meaning are the electrons here and that p orbital both in the plane of the board? Yeah. They both are, right? And so what that means is that if we have some base that comes in and does that protonation, sure, now those electrons can go down and interact with that pi bond, and so we'll end up with this product. And so on the left side, we'll again just keep everything wedged and dashed the same. And so which one is that, E or Z? That is Z, right? So we've got our ethyls on the same side, so we've got our Z product. But we could also have some bond rotation take place, right? And so if we have bond rotation, what we could end up with is our hydrogen on top. And so in that case, now our ethyl, which was wedged, will now be, dashed, will now be wedged. Our methyl, which was wedged, will now be dashed. And we'll just keep everything the same here. So we've got our ethyl group, got our methyl group, and still got our p orbital. Let's make sure we have our positive charges there. Okay, so now we've got our hydrogen flipped to the top side. Is it coplanar with the p orbital?
Yep.
Are these electrons in the same plane as these red p orbitals?
Yep.
Yeah, they're both in the plane of the paper, and so again, what we can have is this come in to form a new pi bond. So in this case, our methyl will be on a dash, ethyl on a wedge, ethyl dash, methyl wedge. And so is that E or Z? That is E. And so you can see here, because we can undergo bond rotation, and basically the electrons from the hydrogen can go into either lobe of the p orbital, well then we can end up getting either product. And so that's why we don't see any stereoselectivity. Yeah.
So that arrow's going to p orbital, not
Yeah.
hard to tell.
Sure. Let's just say that it's going back, as we are known to draw. I'm just trying to show that it's ultimately going to be interacting with an orbital somewhere, and it's going to be that red p orbital that's interacting with. Okay. Did that just shake? Has it been doing that at all? Yeah. Okay.
Beware, Anderson's limit.
Yeah. Okay, so let's just go ahead and kind of summarize. We'll say to summarize. What kind of alkyl halides are we going to be able to do E1 and E1 at? We'll be able to do tertiary and secondary. What about primary and methyl? No, because just like we can't do SN1 at primaries and methyl because the carbocation is too stable, we'll say that we only see E1 at tertiary and secondary. And then furthermore, it is very, very, very messy. Are you ever going to see just an E1 without an S in one? Probably not. I mean, it's possible, right? Because there are certain cases where if we don't, let's say we had a methyl alkyl halide where there are no beta hydrogens, well, you're not going to see either. We'll worry about this flow chart next time. It gets complicated. All right, so I think we're just going to call it good. All right, this is your opportunity to do those evaluations. I didn't know if it was going to be today or Wednesday. So seriously, it means a lot that you get those in. Tell me what you liked, what you didn't like, how I can make things better going forward. I read those very closely and I take them very seriously, and I typically enjoy reading them. So, yeah. And remember, I am giving you a free 5 minutes. So if you sometime 5 minutes today think, oh yeah, I have this 5 minutes because of Professor Wall.
Hey, I missed lecture on Friday, and I looked online and you hadn't posted.
I'll get them
lecture.
up.
Do you know if you do it?
I took the weekend off.
Okay, yeah, definitely. Thanks. You deserve that.
Yeah.
Have a good day.
Thanks, you too.
Is there a podcast last Friday?
Yeah, I'll get everything out.
All right, thank you.